and I'm ready to talk about question 17 on the chi-squared test. Using the same data, my null hypothesis is that there is no difference between dancers and other majors in terms of their ability to ace the tests, which I said gets a score of 85 or better. What is the alternate hypothesis? First of all, I want to remind myself that alternate hypothesis is the same thing as ha. Null hypothesis is the same thing as ho. So an alternate hypothesis is this phrase right here. There is a difference. Between who? Between dancers and other majors. In terms of what? In terms of their test scores. Okay, I could also just repeat what was up there already. Their ability to ace tests. Now I have to go back and look at my data. I know at the top of the page I've got a list of dancers, I've got a list of other majors, and their data is right here. I'm going to go back and look who had an 85 or better. I'll put a check or an X. Dancers had 86, 98, 38, 88, 72, 48, 55, 79, and 85. When I go through that list, it ends up being the dancers with an 85 or better. There were 4 of them. The dancers with 84 or below were 5 of them, and there were 9 dancers total. Went through the other list, I got 10 from the other majors that had a score of 85 or better, 17 that had a score below 85, and 27 of them altogether. My grand total was 14 people that said yes, 22 people that had no, and the total number, if I add 9 plus 27, or 14 plus 22, I should get a total of 36. Remember, your columns should add up going down, and your rows should add up going across as well. Expected data. Have you forgotten it? First, we fill in the totals. 14, 22, 9, 27, and 36. And we're going to use these numbers to solve for the proportion that we would expect would be in each category, if everything was fair. One way to do this is to think about this shortcut. If I'm looking for my expected value of dancers who said yes, I'm going to do it this way. Dance total times the yes total divided by the total. What does that equal? For this example, it equals 9 times 14 divided by 36. I end up with an expected value of 3.5. I repeat the process, or I subtract. 9 minus 3.5 gives me 5.5 expected here. 14 minus 3.5 gives me 10.5 expected here. And 27 minus 10.5 gives me 16.5 expected here. Double check. Do they add up across each row to the total? Do they add up down each column to the total? If it still works, then you've probably done it right. Next part is to calculate the chi-squared. The formula is easy to remember, but also easy to forget. It's observed minus expected squared over expected. I plug in each of the pairs of numbers. Dancers who said yes. My observed was 4. My expected was 3.5. 4 minus 3.5 squared over 3.5. And then I continue. I go down. 5 minus 5.5 squared over 5.5 plus 10 minus 10.5 squared over 10.5 plus 17 minus 16.5 squared over 16.5. Ooh, I lost you there. As I move forward and simplify each one of those, I notice on the top of each fraction, I'm getting the same number. And that happens again and again when you do chi, especially a 2 by 2 chi like this. I get 0.5 squared on the top each time, which works out to be 0.25. But because the denominator is different, I get a different value each time. This one, if I wrote it out, I'm running out of paper here, so let me write it out. Bring in a separate sheet of paper where I go 4 minus 3.5 squared. This is 0.071 plus 0.045 plus 0.024 plus 0.015. When I sum all of those together, I get my grand total for chi. Can't even see it, I'm writing too big now. My grand chi value for this is 0.155. So my final chi value is 0.155. If we round it a little bit differently, that's okay. Some people might have 1.156 or 0.158. As long as we're in the neighborhood, we're okay. And as long as you've shown your work, we can give you partial credit in case you messed up on one of them along the way. The next step of this process is to take this chi number and read the table. We're almost to the end, so I'm just going to keep on talking as we finish this problem on the back page. My chi number was 0.155. Which hypothesis is true? I take this number and I look at the top row of the chart for chi-squared values. I go across until I find two numbers, one that's below, one that's above my chi number. Oops, not again. Watch your decimal point. It's 0.155. That's very close to 0.15, but it's in between these two right here, 0.15 and 0.46. So then I take those two and I go down to the bottom row to see my result. My result is inconclusive. Which hypothesis is true? We have to say it this way. Results are inconclusive. We are not sure which hypothesis is true. Okay? Now, when it comes time to translate this back into plain English, normally we'd say it means that there's a difference if the ha is true, or there's no difference if the ho is true. But when it's inconclusive, we're just going to translate that to this. We need more data. Because we don't have enough, our results are too close to say whether there's a difference or not a difference. But if we got more data, then we could start to analyze whether this was just a fluke, where the dancers performed a little bit different than what we expected, or if this was a typical thing and there is really a difference between the dancers and the other majors. One thing that's interesting looking at this is that even though at the beginning of the problem we said, some of us said that the other majors did better, when I look at the chi table at the bottom of the page and compare it looks like the dancers did better than what was expected, and the other majors did worse, slightly worse than what was expected. They're all very close, but what's interesting is that when we choose that number of 85 or better, that's kind of an arbitrary cutoff, and that means that the results could be different if we had chosen an 86 or a 90 or a 75 or a 60. So always when you're doing statistics, question why they're making those cutoffs, where they are, and what they're hoping, what results they're looking for when they do that. 10 minutes is a long time to listen, so if you're still listening, thank you very much. I hope there's a positive correlation between your study and your final exam score. Good luck.